So hello everyone, my name is SungBin Lee. I'm president of QISCA and I'm also a member of SQRT. So today I'm going to present about the research topic that I've been doing for the last 1 year with my colleagues HeeRyang Choi and Donghyon Ohm. They're all from SQRT members. So this research has been part of the SQRT research team as one of the internships. So we are currently preparing archive manuscripts and will be published like maybe within hopefully soon. So okay, I'll present my research topics. So topic is about random quantum circuits, pseudo-randomness, and scalable projective entangled parasitic representations. It's kind of similar to Professor Hyuk-Jung Won's presentation about 2 hours ago, but obviously I'm not a professor, so I'm not an expert. So there are several many flaws. So I will be very much appreciative if you can just point out those points. Okay, so I'll talk about first what random circuit is. So random quantum circuits, by definition, is very simple. It is designed to be hard for classical computers, but this is for quantum computers. Because if you can design those problems, and if you can perform those experiments on a large scale with real quantum computers, then we can expect to outcome every classical supercomputers. So that's basically proving quantum supremacy in real worlds. So it's basically a computational analog of Bell's test, which tests between whether quantum mechanics or local hidden variable theory is correct. So random quantum circuit explores the Hilbert space as quickly as possible by generating large entanglements quickly and fastly. So first you apply single cubic gates here on these green dots and 2 cubic gates on this 2 blue lines. So you entangle gates by just entangling 2 cubic gates here between 2 qubits. Okay, so and after you create large entanglements by just putting large 2 cubic gates, and after measuring them in computational basis, then you're going to have some bit-string probabilities. If you obtain those probabilities and compare with ideal ones, then you can compute several statistical flaws, and you can test whether you have chosen true random quantum circuits. So these experiments are known to lie in this region. So for quantum supremacy experiment to hold, we need 3 conditions. First, it has to be classically hard, obviously. If it's classically easy, then that's no quantum supremacy. Second, it needs to be efficiently verifiable. If you cannot verify experiment, then that's basically useless. And thirdly, it has to be NISQ, meaning that noisy quantum computers has to be able to perform those experiments. So random circuits, sampling with random quantum circuits lies in these 2 reasons. It is classically hard and NISQable. However, it is not efficiently verifiable as far as we know. So that's the reason why there's still some kind of controversies in quantum supremacy experiments first performed by Google in 2019, published in Nature. About 7,000 citations by now, I guess. On the contrary, the Shor's algorithm lies in this region, where it is classically hard and efficiently verifiable, meaning it is an NP problem. However, it's not NISQable. Obviously, if you can perform Shor's algorithm, we need like logical error qubits with above fault tolerant levels, like maybe up to hundreds or thousands of logical qubits. That's not going to be possible. So that's the reason why we're researching random quantum circuits. So what is the goal of random quantum circuits? The goal of random quantum circuits is to generate Haar random states. Haar random states defined as random unitary matrix spaces given as the Haar measure. So since it's unitary, then the probability has to be preserved through the. So while calculating the probability distribution, the Haar random states are given as delta, like sum over all the probability minus 1. So that's the constraints. So if you compute these numerators and denominators, and you get exponential decaying parameters according to the bit-string probability P. So for classical random, the distribution is given as uniform random, meaning that just probability is all given over 1/2 to the n. So that's here, just uniform. For Haar random states, since according to these derivations, the probability decays exponentially, meaning that it has some kind of heavy outcomes, meaning large probabilities. So we call this term anti-concentrated Haar random, contrary to classical randoms. There are several other differences. For example, there are also differences in XCB. XCB defined as these parameters. What you just have to know is if you generate true Haar random states, then the XCB is 1. While for classical random, it is 0. There are also several different parts like Kate movements, meaning Kate, the Kate power of the average Kate power, meaning the Kate cumulant of the entire distribution. It has to be K factorial if you give the exponential value. So long story short, Haar random states are different from classical random states because, and that's the reason why we're using random quantum circuits, because it's different from classical random. Okay, then how hard random quantum circuits is? I will not go into the details of like complexity theory part here in the quantum sampling with random quantum circuits. What you all just have to know is that approximately sampling random quantum circuits, meaning approximate up to some multiplicative error C, is approximate gap P hard, which is about similar to sharp P problem, which is harder than polynomial hierarchy, which is again harder than approximating sharp P problems. Sharp P problems are much harder than MP, generally known. So it basically means that even approximating samplings are very hard compared to like classical counterparts. So for anyone who is interested, we can prove this relationship with two methods. First, we use Stockmeyer's algorithm. So Stockmeyer's algorithm basically confessed that approximating sharp P problem is confined in the third level of the polynomial hierarchy. Polynomial hierarchy defined as MP oracle over MP. So if you have like ideal MP oracles that can solve MP problems, then you can have sigma 2 power of complexity classes. So it means approximating sharp P problems is confined to sigma level 3, which is obviously smaller than the entire polynomial hierarchy with infinite numbers of MP oracles. However, according to Toda's theorem, polynomial hierarchy itself is going to be confined in the polynomial of sharp P. So basically, we can prove these relationships in the assumption that P is not equal to MP, which is generally believed to be true. It means that if P is not equal to MP, then approximating random quantum circuits is just basically very hard. So that's why we are doing random quantum circuits, because it has strong complexity theory evidence that it is classically hard, meaning it has strong evidence that it lies in this region. And obviously, we can perform RCS with noisy quantum computers because we can just apply gates and sample from the output bit strings, and that's all. So that's the reason why we are doing random quantum circuits. But the problem with as I told you, random quantum circuits are very hard, but there have been previous attempts to classically simulate random quantum circuits. I will skip the details. I will just sketch a few. So in 2022, published in PLL, Chinese Academy of Sciences have performed 3D tensor network simulations on random quantum circuits. So they have used 53 qubits, meaning this layer is 53 qubits with 20 circuit depths. They just constructed the entire quantum circuits with 512 GPUs. That takes like 15 hours. And they achieved better fidelity than Google's experiment in 2019. Obviously, their methods are not scalable. If Google have used 54 qubits, then they cannot use it. I actually asked the corresponding author of this paper, and he did confirm that it's not possible. Okay, so also for scalability, last year, Simon's foundations in United States had used approximate de-merger algorithms to also simulate random quantum circuits. They have achieved better fidelity in some situations, meaning close simulation, where you just compute the single bit strings. They achieve 2.4% error rate per 2 qubit gates compared to 2.8% of Google. However, their limitation is that if they open up every bit strings, then they have much higher error rates. So what we believe is that if we use efficient tensor network algorithms like two-dimensional in particular, then we can achieve both scalability and accuracy. So that's what we are doing for the past year. So we are using PEPS, projective entangled pair states, as a tensor network ansatz of random quantum circuits. So PEPS is basically defined as the network of two-dimensional network of 5-dimensional tensors, given as this follows. So since it is a 2D circuit, it's generally naturally a good ansatz. However, the cons of projected PEPS is that PEPS has no known canonical form, unlike one-dimensional MPS used by Thomas Araya last year. So we have to define quasi-canonical forms for classical simulations to be plausible. So we use Vida gauges to approximately impose canonical form on PEPSIS. So the Vida gauge is defined as this follows. So if you decompose the entire two-dimensional tensor network into the gammas and lambda tensors, then we can impose this kind of orthonormalization condition on each gammas and lambdas after every iterations. So if we impose this kind of Vida gauge conditions, then we can contract the entire tensor network by just contracting the inner lambda tensors due to these relations. Of course, this is approximate because it is two-dimensional. However, it is a good approximate given by this PLX quantum paper published this year who have simulate IBM's quantum utility experiments up to 127 qubits. So we also use simple update methods, which updates two qubit gates variationally and not variationally, approximately, because if you update it exactly, then the computational cost will be infeasible. It is basically a natural fit for Vida gauge defined as follows. After two qubit gate operations, obviously this orthonormalization condition fails because gammas and lambdas changes. So you have to reimpose the Vida gauge conditions by just taking an identity matrix as a simple update. It is called a simple update gauging, frequently used in tensor network methods. So that's how we can impose these two-dimensional tensor networks and simulate two-dimensional random quantum circuits. Okay, so wait a second. So these are the so we first proved that PEPS is an accurate random quantum circuit and such by comparing several physical quantities. We first compare the entanglement entropy spectrum for different two qubit gate sets. So two qubit gates we just control Z gates, fermionic simulations, and just random U4, meaning two qubit Haar gates. So we can see that they all coincides nice. They all each resembles each other for exact simulation. So PEPS simulation is a good approximation of the exact simulation. Similar for a B-string probability distribution, I already confessed that random quantum circuits have distributions close to Potter-Thomas distributions, meaning this exponential decaying parameter defined as this dotted line. So we can see that for both exact and PEPS simulations, all of the distribution converges to the Potter-Thomas distribution as the circuit depth grows and the simulation accuracy increases. So this chi represents the bond dimension of tensor networks and represents the accuracy of the simulation results. So as the simulation becomes more accurate, all of the distribution converges down to the Potter-Thomas distribution, as it should be. And also for the Kate moments, as I already told you, the Kate moments of the random quantum circuit has to be K factorial, and we also converge down to the up to circuit depth 20 with PEPS simulations if you increase the bond dimensions down to D. So these are the key factors that we show that PEPS is an accurate ansatz of random quantum circuits, even though it is approximate, because we can only approximate simulations for general quantum circuits outside of Guttesman neo-zero, as Professor Hyuk-Jung Won today told us. But even this approximate simulation still give us a good ansatz of what's truly happening. Okay, so one interesting thing about this result is shows that even these random quantum circuits, even though if it only use two qubit gates, even for large systems, that it cannot be distinguished with exact Haar random states up to 4 moments. So this orange line is k equals 4. So we call it 4 design in terms of technical perspectives. What it just basically means is that it is polynomially hard to distinguish the true Haar random states and the random states we generated with 2 qubit gates. But on the contrary, if you focus on the entanglement spectrum, then we can see that while control Z gates have degeneracy, so the color represents degeneracy. This G numbers the degeneracy in singular values. We can see the control Z gates are highly degenerate. Fermionic simulations are somewhat degenerate, but 2 qubit Haar is what closest we can get to the Haar random states, shows no degeneracy. So it means that even though it cannot be distinguished by B-string samplings, it can be distinguished with entanglement spectrum entropies. So it means that random quantum circuits has pseudo-randomness, meaning not truly Haar random, but close to it. And pseudo-entanglement, meaning that even though it is pseudo-random, it has different entanglement perspectives. So that's a kind of interesting part we were able to find without where the experiments cannot, because we cannot measure entanglements with experiments unless we do state tomography, which is exponentially hard. Okay, so we also compare the fidelities and cross-entropy benchmark, because computing fidelity is exponentially hard for general quantum circuits, because to compute the fidelity, you have to know the ideal states, and to know the ideal state, you have to get the entire state vector simulations, which is just physically unfeasible. So in experiments, we usually use cross-entropy benchmarking, short for XCB, to approximate the fidelity. So Google in 2019, Google approximate that fidelity is same as XCB. Last year, the Simons Foundation take controversial arguments that fidelity is actually a square root of XCB. And like I believe just 2 months ago, Google also refuted this argument by saying that this only holds that low error limits, meaning like close to ideal simulations or ideal experiments, and it also undergoes phase transition. What we discovered is that if we plot the fidelity versus XCB, so x-axis is a fidelity and y-axis is XCB, if we increase the simulation accuracy, then the fidelity and XCB is identical in high fidelity limit, meaning low error limits, and it converges down to the square root limit, meaning this blue dotted line, as the simulation as the fidelity decreases. So it means that actually the both statements are correct in their different respective fields at low and high error limits. So that's what we have found by our accurate PEP simulations. We also found that there is a strong correlation between the two. So we have collapses down the entire fidelity into a universal plot by just using a exponential extrapolation, and we discovered that if we fix the theta and phi of the 2 cubic gate configurations, then all of the lines collapses into a single line for both fidelities and XCBs with same A and B. So A and B is a parameter of theta and phi defined as this follows. So if we fix these values, so if we fix down theta and phi, then they all share the same universal behavior, meaning that fidelities and XCBs are strongly correlated. So it basically means that XCB is actually a good measure of fidelity if we compute XCBs accurately. So afterwards, we developed tensor network methods to compute approximate the fidelity. So since it's a simulation, we can develop methods that can approximately calculate the fidelity. We also use Vida gauge conditions here and only contract down this discarded singular values of lambda tensors. We compare down the exact fidelities and concluded that so these dotted error bars are exact fidelities, and the shaded areas are approximate fidelities computed by tensor network algorithms. And we determined that they are actually a good approximate of each other when the fidelity per qubit is higher than 50%. So it is a qubit system. Fidelity below 50% is meaningless. Above 50%, they collapses wonderfully for every circumstance, for every 2 cubic gate simulations. So we have cranked up the size up to 8 by 8 qubits. So this green line is the DMR algorithms published at PLX Quantum last year. Yeah, so these are these algorithms. So what we discovered is our PEP simulations have much better scaling in terms of same bond dimensions. So at same bond dimensions, then our PEP algorithms have much steep decrease in error per gate rest. So it is much more accurate. And we can also go below Google's experiment threshold at certain amount of bond dimensions given by this gray shaded area. So since PEPs is scalable, we can go up to like qubits up to 10,000 qubits. So you can see that n is of 10,000, 10 to the power of 4. So in this case, by 100 by 100 circuits, what we basically discovered is that they all collapses into a single line if the quantum circuit reaches a certain threshold. So as the size of the circuit increases, then it becomes exponentially slow, meaning that there's a universal behavior in random quantum circuits, and we can extrapolate this to estimate the performance of PEP simulations. So how can we estimate the performance? Meaning, what circuit depth should we focus on? As Professor Hyuk-Jun Kwon mentioned, the most important depths in random quantum circuits is log depths, meaning that given as the logarithm of the number of qubits, So we have discovered, we have performed our PEP simulations on 2 log and depths. What we discovered is that our PEP simulations were able to simulate the hardest random quantum circuit configurations up to 1% error rates, up to 10,000 qubits if you use the best supercomputer in the world. So this is the counter plot. If you use the frontier with 700 petabytes of memory, then you can go up to 10,000 qubits with error rate of 1%. So that's the reason. So it is possible because we can efficiently estimate the fidelity with PEPS algorithms. So in conclusion, we have discovered that random quantum circuits has pseudo-randomness and pseudo-entangled. We have also strongly have good impression that there's a strong correlation between fidelity and XCB. We have also proved that PEPS is a scalable ansatz that can achieve finite fidelity, and we are going to need 10,000 qubits to achieve fidelity quantum advantage in locked noisy random quantum circuits. So thank you for listening to my presentation.